Okay, chapter 5, chemical reactions. Chemical reactions happen all over the place. They happen all around us. Chemical reactions are basically just describing a chemical process. Usually the chemical reactions that we're talking about in this class will describe where we started and where we ended, and we're not going to focus really much at all about what happens in the middle. Organic chemistry, you focus a lot on what happens in the middle. So these chemical equations are sort of like if you're describing a football play to somebody or the outcome of a sporting event. If you drop your phone, food recipes, etc. The way that we keep track of chemical reactions with equations has this general form where we've got our reactants on the left side. Reactants, believe it or not, react. So those two things, you put them together, something happens, and out the other side comes the products, just what's produced. I will often talk about these interchangeably as left and right, and reactants and products. You should know reactants and products as their name. And then the little arrow in the middle, just letting you know that we're headed in the right direction. Literally the right direction. Sometimes it happens both ways, and we'll get to those later in the class. But not today. So some examples of word equations. I dropped my phone, it hit a rock, now my screen is cracked. So the way that we would describe this in like a word version of a chemical reaction, phone screen plus rock turns into cracked screen plus rock. Right? The rock was not damaged in the process. No rocks were harmed in the making of this example. The way that we would do this with chemical reactions, methane gas, this is the gas that comes out of your stove if you have a gas stove and you're on a city supply. Methane gas reacts with oxygen in the air. It burns, it forms carbon dioxide and water. The water is not so bad. It's gaseous water. The carbon dioxide, this is one of the reasons that you don't want to cook in a poorly ventilated space, because that carbon dioxide will build up and it's bad for you in large amounts. So chemical equations represent these chemical reactions. Our substances on the left side are reactants, the substances on the right side are products, and will often indicate physical state as well, which we'll see in a couple slides, all those things. So for example, this is the equation that we were talking about on the previous slide. Our CH4, this is our methane. It's a gas. Our oxygen is O2, also a gas. We know it's O2 because Fonkel brick ship are H7, or horses need oats for clear brown eyes. Oxygen normally exists as O2. And then we've got our carbon dioxide and our water. Typically, we're going to represent things with the formula rather than with the words or the names. Partly because the formula is just more compact, but it also lets us do some other stuff more easily. You will not always be given the formula. Sometimes you will be given just the names of the things and you will be expected to come up with the formula. So this is where our nomenclature knowledge starts to become a little bit more crucial. To be able to access some of these problems, you have to know the nomenclature. We've got a couple types of chemical equations as well. So we've got a skeleton or skeletal equation. And our skeletal equation only shows the formula for the reactants and the products, just the formulas. Another way of talking about it is our skeletal equation is the bare bones. It's the very minimum amount that you need to get by. So, for example, this reaction that we saw before, we substitute in the chemical formulas for the names. And then these symbols that come after in the parentheses, in this case, they're all G, which is not for good, it's for gas. So this is a table from our online book. We've got the plus. You just separate all your different chemicals with a plus if they're on the same side. We've got our reaction arrow. We've also got a double-headed reaction arrow, so this means that it can go both ways. There are some reactions that do that. We've got solid, liquid, gas, and aqueous. Aqueous means that it's dissolved in water. So like if we're doing a reaction in a liquid, in water, then we would have AQ behind anything that's dissolved in the water. So like simple syrup or like a salt gargle, the salt and the sugar in those would be AQ because they're dissolved in the water. One of those things that we can unlock with writing out the chemical equations is balancing equations. So if we look at this equation, this is the same one that we were looking at before, we can see, looking at our oxygen on the left side, we've got 2 oxygen atoms. On the right side, we've got 2 oxygen atoms in our CO2, and we also have one in our H2O. So we started with 2, and the way we've got it written out, we ended with 3. And some of you might see how this is a problem. Where did that extra oxygen come from? This violates the law of conservation of mass. So we can't have an unequal amount of one atom on the left side versus the right side. We have to have the same amount of atoms of each element on both sides. And if we write it out with the chemical equations rather than the names, we can easily see how many of each type of thing we have, each element we have. We also have an imbalance with our hydrogen atoms. We've got 4 hydrogen atoms on our reactant side, and we only have 2 hydrogen atoms on our product side. So to solve these issues, we're going to come up with a balanced equation. Our balanced equation will have equal number of each atom of each element on both sides. This is a basic skill in chemistry, as are a lot of things in this class. It's general chemistry. It's foundational to a lot of the other chemistry that you'll learn. In order to balance an equation, we can insert coefficients. So the coefficients are like that 6 or 2 or 7 that we saw in front of the hydrate on the previous chapter. So the coefficients go in front. Coefficients go in front of chemicals. We cannot change, we should not change the subscripts, these little numbers that follow our number of atoms in a compound, because then that would change the chemical. So we want to stick with the chemicals that we've got and just adjust the amount that we're adding into the mixture. And we've got a set of rules for doing this balancing process. Again, we're only adding coefficients in front of the chemicals. They're always going to be whole numbers in this class. So to write balanced chemical equations, the first step is we need the correct chemical formulas. Sometimes you'll be given them, other times you might be starting with names. So this first step is basically all of nomenclature. So we're just assuming, no thank you Siri, goodbye. We're just assuming that you know the nomenclature. That's sort of just like a baseline assumption moving forward. You won't always be required to know the nomenclature. Sometimes you will be given the chemical formulas. Then you're going to write out this skeletal equation. The things that react go on the left, the products go on the right, and you will have to pick apart sometimes what are the things that go on the left, what are the things that go on the right. So we do have some problem-solving elements that are coming into play. Once we've got our bare bones, once we've got our skeletal equation, then we're going to balance things that occur in one compound on both sides of the equation. So things that, if we change them, could potentially change other things, and they're on both sides. If we've got more than one such element, typically the strategy would be to balance metals first. Then if we've got elements that occur as a free element, it's just that element. So for example, like O2 or H2 or zinc metal, for example. With those, we can change the coefficient that's in front of the chemical. We can change that up or down as much as we want to, and it's not going to affect anything else. So that's why we're going to leave that for last. It's the easiest to adjust. It's not going to throw off the balance for other things. And then if we have coefficient fractions, which can happen, there's a couple of instances where we might get coefficient fractions on our journey to balancing the chemical equation. We're going to change those to whole numbers by multiplying everything by a number, usually 2. Okay, so let's get to this very soon. We would also at the end, especially early on when you don't have a lot of practice with this, it's always a good idea to just check and make sure that it's balanced. So you'd go through, look at the left side, how many of carbons do I have? Look at the right side, how many carbons do I have? Are they equal? They're equal, great. How many hydrogens? How many hydrogens? Just for all the elements, just check on both sides. And then as a review, we do change the coefficients to balance a chemical reaction. For example, this 6 that I've put in front of this H2O, we do not change the subscripts, like the little 2 that's in H2O. And again, our goal is mass is conserved. So we've got the same pieces before and after. It's sort of like if you have a Lego set that you just kind of made stuff up, where you like, hey, I want to repurpose this. You tear it apart, you build it into something else, and hopefully you don't lose any pieces or find any new pieces along the way. We want to take it apart and put it together and use all the pieces. We're doing a similar thing with chemical equations. Okay, for example, we want to write a balanced chemical equation for the combustion reaction. That's a little tidbit of extra knowledge that we might use at some point. It's the reaction of gaseous C2H6 and gaseous oxygen to form gaseous carbon dioxide and gaseous water. What's the words that signal where we put our arrow? To form. So to form is the signal word. This is indicating our arrow. So our reactants are the C2H6 and the oxygen. C2H6 because we don't have the nomenclature tools for you to know what that's called. It's ethane. And then our other reactant is gaseous oxygen. What's our formula for oxygen? O2. So we've got O2. This is also a gas. Those words to form means we write in our arrow, and then we've got carbon dioxide. We've got a prefix in there, the di prefix. So this is a molecular compound. Carbon and oxygen are also nonmetals. We don't have a prefix in front of our carbon, so it's just one carbon. We've got a prefix of di in front of our oxygen, so that means we've got 2 oxygens. This is also a gas, and then we've got water, which is the common name for H2O, also called hydrogen monoxide. Okay, so we've got our skeletal equation, and now we need to start balancing. So we're going to look for things that are in one compound on both sides. What's one of those 2 things? What's an element that's on both sides and it's in a compound? It's not by itself. Carbon. So carbon, we've got in our C2H6. We also have it in our CO2. How many carbons do we have on the reactant side? 2. We have 2 because of our subscript of 2 in C2H6. How many carbons do we have on the right side? 1. Yeah, we've got 1 on our product side. Obviously those don't match, so we need to bump those numbers up. We're going to put a coefficient of 2 in front of our CO2 to double the amount of carbon, and now we've got 2 carbons. So our carbon's balanced. What's the other thing that's in one compound on both sides? H, hydrogen, right? It's in C2H6 it's also in H2O. So we can balance our hydrogen. Our hydrogen, we've got 6 on the reactant side, and we've got 2 on the product side. So how are we going to get the product side to 6 hydrogens? We'd put a coefficient of 3 in front of our H2O. Because this 3 coefficient times the subscript of 2 gives us 6 hydrogens in total. What's the last thing that we have to balance? Yeah, it's our oxygen. So we're going to balance our oxygen last. We've got 2 oxygens on the reactant side in our O2. We've got 2 times 2 from our CO2. And we've also got oxygen in our H2O. We've got 3 H2Os. So we've got 2 times 2 plus 3. So we've got 7 oxygens on the right side. So we can adjust our O2 to get our number of oxygens up to 7. What would we have to multiply 2 by to get to 7? Three and a half. Or 7 halves is the same as 3.5, or 3.5. So when we do that, our oxygens are now balanced. Is this our answer? Can I have half of an O2? No, you can't have half of an O2 because they're all oxygen pieces, right? You can't just like slice that in half like you can a sandwich. So in order to get this balanced, we have to multiply by something that'll get rid of this 2, that'll turn this 3.5 into a whole number. So we're going to multiply everything by 2. So all of our coefficients get multiplied by 2. And since we're multiplying everything by 2, everything's shifting up. It's already balanced. So we're just shifting the amount of everything. We're not changing the balance. It's still balanced. There's probably another way that you can do this without putting a coefficient that's got a fraction in it in front. But it's going to take longer than just multiplying all those numbers by 2. So our balanced chemical equation will be 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. And then if we wanted to, we can check and make sure that it's still balanced. So let's do that real quick. So we've got our carbon in C2H6. We've got 2 of them in there. We've got 2 of those. So 2 times 2, we've got 4 carbons. On the right side, we've got 4 carbons from our 4 CO2s. For our hydrogens, we've got 6 in each of our ethanes. So 2 times 6, we've got 12. We've got 6 times 2 for 12 from our waters on the product side. Our oxygen is a little bit more complicated of a story. We've got 14 on the reactant side. We've got 4 times 2 for 8, plus another 6. 8 plus 6 is 14. So we're all balanced still. Any questions about any of the steps of that process? Cool. Here's a different type of balancing equation. We've got aqueous solutions of lead 2 nitrate and sodium chloride that are mixed. The products of the reaction are an aqueous solution of sodium nitrate and a solid precipitate of lead 2 chloride. write the balanced chemical equation for this reaction. So we've got lead 2 nitrate. We're told that that's aqueous. We also have sodium chloride, also aqueous. So our lead 2, this 2 here, means that we've got a charge of 2 plus on our lead. So this is Pb2 plus, and nitrate is NO3 minus. When we crisscross this to figure out the chemical formula, we've got PbNO3 2. And this is aqueous, so we put a little AQ in parentheses behind it. We also have sodium chloride. Sodium, when it forms an ion, is a 1 plus. Chlorine, when it forms an ion, is a 1 minus. So we've got our old friend NaCl, sodium chloride table salt. So those are our reactants, because those are the things that are mixed. And then we're told explicitly the products. So the products, those go on the right side of the arrow, are sodium nitrate. So our sodium and our nitrate are going together. It's a 1 plus and a 1 minus. So those will go together in a 1 to 1. So we've got NaNO3. And we're told that this is an aqueous solution. Our other product is a solid precipitate. A precipitate is just a solid that forms from this sort of combination of things. Scooch everything over so I've got some more room. And our solid precipitate is lead 2 chloride. So it's our Pb2 plus and our chloride. Just like with our PbNO3 we're going to end up with 2 chlorides. So PbCl2, and this one is a solid. So we've got a skeletal equation. Part of the reason that I show you this example is because it doesn't follow our rules quite as nicely as the previous example. So our rule was we wanted to balance something that's in one thing on both sides, one compound on both sides. Okay, so let's look for things that are in one compound on both sides. For lead, we've got lead in our lead 2 nitrate. It's also in our lead 2 chloride. Okay, so we could balance that. We've got nitrate. Generally, we're going to be treating polyatomic groups just as one unit. So we've got our nitrate that's in this compound. It's also in this compound, so that's in one thing on both sides. We've also got sodium, which is in one thing. Oh, look, that's on one thing in both sides. And we've also got chlorine, which is also in just one thing on both sides. So where do we start? We can start with, as the problem mentioned, balancing metals first. I like to balance these ones a little differently. So I'm just going to look for what's something that's different on both sides. Can somebody give me an example of a chemical that's different on both sides? In terms of the number, not balanced. 2 chlorides. Okay, so we've identified that our chlorines are different. We've got 1 chlorine on the reactant side. We've got 2 on the product side. To balance that, we're going to put a 2 in front of our NaCl. So now that means that we've got 2 chlorines. When we add this 2 in front of our NaCl, that didn't just change our chlorine, right? It changed something else. What was the other thing it changed? Sodium. So we're going to follow our path of unbalancing things by moving on to the sodium next. So we have 2 sodiums now on the reactant side. We've only got 1 on the product side. So we're going to need a coefficient of 2 in front of our NaNO3. And when we do that, we've balanced our sodium, but we've also changed our NO3, our nitrate. So we'll balance nitrate next. We've got 2 on the product side. That's the thing that we just changed. And if we look at our reactant side, look at that, we've got 2 nitrates. So that one we just happened to balance. So we've kind of hit a dead end. So we'll just check on everything else. So our lead is the last thing that we didn't balance, and lead is already balanced. So it's a 1 and 1. So the way that I like to solve these ones, where everything is in one thing on both sides, one compound on both sides, just find something that's different. We could have started with our nitrate too. We started with the chlorine. We balanced that. That disrupted our sodium, so we balanced our sodium next. When we balanced our sodium, that changed the number of nitrates that we had, and coincidentally, that meant that our nitrates were balanced. This doesn't always work. Sometimes it ends up a little bit messy. We don't encounter those very much in this class, and so this strategy is quite effective for balancing chemical equations. Questions about that process? Cool. One for you to try. Write a balanced equation for the reaction of aqueous lead-2 sulfate with aqueous potassium iodide to form solid lead-2 iodide and aqueous potassium sulfate. So I'll give you the rest of class to solve this, and then we will pick up here with the solution at the start of next class on Monday.